In this video, we will be looking at one of the useful applications of having a Lewis dot structure, that is, determining the bond energies and using those bond energies to determine the amount of energy that we need to either put into a reaction or that we can expect to get out of a reaction. Most chemical reactions involve the breaking of bonds in the reactants and the formation of new bonds in the products. The enthalpy of reaction, which is represented with delta H reaction, is the amount of energy that either goes into or comes out of a chemical reaction. It can be estimated by comparing the cost of breaking the old bonds, those in the reactants, and the energy that's incoming from making new bonds in the reactants. The amount of energy in a gaseous state that it takes to break 1 mole of bonds in a compound is called the bond energy. These bond energies are typically averaged values from several different molecules that have similar structures. In general, the more electrons two atoms share, the stronger the covalent bond is going to be. We can compare some of these values. For example, a carbon-carbon triple bond has a bond energy, or the amount of energy that is required to break the bond, is 837 kilojoules per mole on average for carbon-carbon triple bonds. For carbon-carbon double bonds, this energy to break a carbon-carbon double bond on average is 611 kilojoules per mole. For a carbon-carbon single bond, it's 347 kilojoules per mole. Again, this is the average amount of energy for a bond. Depending on what else is bound to the carbon, these numbers can change, but most of the time the bond energy values give you a good idea of the energy for the particular bond that you're looking at. We see a similar trend in a carbon-nitrogen series of bonds, where the triple bond has more energy required to break it than the double, which requires more energy than the single. Also, generally, the shorter the covalent bond, the stronger the bond is going to be. It's most convenient to do a comparison of similar types of bonds. So looking at like a bromine to fluorine, bromine to chlorine, and bromine to bromine bond, if you remember from our atomic radii, fluorine is smaller than chlorine, which is smaller than bromine. So because fluorine is smaller than chlorine, the bond strength here, which is the amount of energy that is required to break the bond, is greater than in the bromine-chlorine bond, which itself is greater than the bromine-bromine bond. So as the bonds get longer, they get easier to break. So bonds get weaker as we go down the column, and bonds get stronger as we go across a period. These two trends here are consistent with our atomic radii trends. This here is the type of table you would commonly come across when you're looking up bond energies. They're most often categorized by one of your atoms. So in this case, this would be hydrogen bound to other things. You can see that as you go down the periodic table, fluorine, chlorine, bromine, the bond gets weaker, so the bond energy decreases. It becomes easier to break the bond. Similarly, as we pointed out before, as you increase the number of bonds, going single bond, double bond, triple bond, the bond gets stronger. So these bonds themselves are categorized by one atom bound to something else. The value in those tables, again, is an averaged value of many different types of molecules that have the particular bond that you're working with. The actual bond energy of the molecule that you're working with for a particular chemical bond will depend on the surrounding atoms and other factors. We often use the average bond energies to estimate delta H reactions for chemical reactions that we're working with new components. These values work best when all the reactants and products are in the gas state. The reason for this is that you can have intermolecular interactions between different molecules which can either stabilize or destabilize your entire set, and those interactions are going to be stronger in either the solid or the liquid phase. In all cases, whenever you break a bond, it is an endothermic process. You have to put energy in to break the bond. So always breaking bonds is going to have a positive delta H, meaning that you have to put energy into it to break the bond. Whenever you make a bond, it's the reverse process. So if bond breaking is endothermic, then bond making must naturally be exothermic, meaning that energy is released whenever bonds are made. So the delta H value for making a bond will be negative. To find the change in energy for a reaction, we would add up all the bonds broken plus all the bonds formed using the correct sign for each. So if we are breaking a bond, over here we have to use positive delta H values, and if we are making bonds, then we would use the negative of the value we find in the tables. Add them all up, and you would get the change in enthalpy, or the amount of energy that is either required for the reaction to take place, or that the reaction will give off as it takes place.